So the first example is one we covered last Friday. So I'm not going to formally have you take notes again on this. And for those who weren't in class, they can go to the recording from last Friday to see the, to look at the discussion of it. But we wanted to approximate the cube root of x by a second degree Taylor polynomial about a equals 8. And we used a equals 8 because the cube root of 8 is 2. And that meant when we constructed the Taylor polynomial, and of course, I always have the formula sheet there. We used our Taylor polynomial formula, right? So we have to compute derivatives of the cube root of x and evaluate those derivatives at a equals 8. We did that, and since it's a second degree Taylor polynomial, we can stop at the second derivative because then the second derivative of 8, which is negative 2 over 888, that term is right here, right? So we get our second degree Taylor polynomial, and here it is. And then we want to know how accurate the approximation is when x was between 7 and 9. Well, so for this, we're going to use Taylor's inequality. Okay, we're going to use Taylor's inequality to answer this question. So Taylor's inequality, as you recall, was given on the formula sheet at the bottom, and it works very much like your section 5.9 numerical integration formulas in terms of like the error bounds. What you're doing with Taylor's inequality is you're trying to get a bound on the error in your approximation. The error in your approximation, sometimes called the remainder, is the difference between the function itself and the approximation, your Taylor polynomial approximation, t sub n, of the function. So, of course, there's going to be a difference between the actual function and the polynomial approximation, t sub n. But then, if you want to know how accurate your approximation is for certain values of x, the error bound is defined as m over n plus 1 factorial times the absolute value of x minus a to the n plus first. Well, in our case, as we discussed last Friday, we get a second degree Taylor polynomial, so that means n was 2. Okay? And then finding the m value, well, m is greater than or equal to the absolute value, in this case, of the third derivative when x is between 7 and 9. Okay, so that x minus a over less than or equal to d can be re-expressed as x minus 8 less than or equal to d being 1, because then x minus 8 is less than or equal to 1 and greater than or equal to negative 1, and so therefore x is greater, hold on here, yeah, x is greater than or equal to 7 and less than or equal to 9. So in the Taylor series inequality formula, when they have this, the absolute value of the n plus first derivative is less than or equal to m for when the absolute value of x minus a is less than or equal to d, that's equivalent to just saying when x is less than or equal to a number, or x greater than or equal to a number. I mean, the absolute value of x minus a less than or equal to d can be written then as x is between two values. And in this case, we had x's between 7 and 9. That's what we had for this problem, right? We wanted to know how accurate our second-degree Taylor polynomial approximation is when x is between 7 and 9. But that equivalently can be expressed as the absolute value of x minus 8. And you notice 8 is the a. Okay, the absolute value of x minus 8 is less than or equal to 1. Okay, so really you don't need to concern yourself too much with this, absolute value of x minus a less than or equal to d part of the theorem, because when they give the interval that they're interested in, it naturally will well, I want to say it'll actually sync with how they stated in the theorem. Okay, are there any questions on that before we move on? I don't want you to be confused at all by the inequality. Okay, all right, so let's move on then. So what we did then was, we found the second-degree Taylor polynomial, and then we applied Taylor's inequality. And we showed that this third derivative of x, the absolute value of the third derivative of x, and remember f of x is x to the third derivative, it was 10/27 times x to the negative 8/3. And of course, the absolute value of that third derivative would just be the third derivative, because this third derivative is positive when x is between 7 and 9. But the key here then again, we need to figure out what m is, right? Based on this criteria. Well, you have to find out then where your third derivative is maximized over your interval. And we computed the third derivative, which was 10/27 times 1 over x to the 8/3 power. But we note that that third derivative decreases with x. It's a decreasing function with x. And because of that, because our third derivative decreases with x, that means that the third derivative would be maximized when x is 7. Okay, the left endpoint of that interval. And therefore, that's why we choose m to be 10/27 times 7 times, that's why we choose m to be equal to 10/27 times 7 to the negative 8/3 power. Okay, and so I'm just recapping this, particularly this Taylor inequality part for this problem, just to make sure you're comfortable with it. And now that we know what m is, we know what m is, 10/27, we have that. We have 3 factorial in the denominator because that's 2 plus 1 factorial. The x minus 8 part, the absolute value of x minus 8 is raised to the third power. And then the largest that could ever be is 1, because we're restricting x to be between 7 and 9. And so therefore we get an error bound. We get an error bound here. And that error bound is going to be equal to 0.00035. And therefore, if we restrict x to be between 7 and 9, and we approximate the cube root of x with the Taylor polynomial, second-degree Taylor polynomial of x, it will have this level of accuracy. And what was done here, of course, is they graphed, this is just an illustrative figure, but what they're doing, you can see the accuracy is pretty good. And what they've done is they've graphed the cube root of x function and that second-degree Taylor polynomial on the same picture. And a equals 8 falls, they're skipping by increments of 3 here along the x-axis. So 9 is right here, and 8 is here. And so this value here at a equals 8 is at a equals 8, right? That's where the Taylor polynomial and the cube root of x agree perfectly. And then the Taylor polynomial and the cube root of x will, the Taylor polynomial, second degree Taylor polynomial, will approximate the cube root of x then. And it does it pretty well over the interval from 7 to 9. But obviously, as you move away from the a equals 8 value, as you get like far away from 8, like if you get over here close to 0, or past 3 right here, you can see that the cube root of x and the second degree Taylor polynomial, the approximation starts to fail, right? All right, so I just wanted to, but we talked about this, but I just wanted to recap that Taylor inequality part. So the Taylor inequality, remember, how the hardest part is figuring out, what is M? What is M? And to figure out what M is, you have to compute your derivative. Okay, so in this case, it was the third derivative. And then ask yourself, is my derivative, okay, whether it's the third derivative, fourth derivative, whatever derivative it is my derivative decreasing with x or increasing with x? So if the derivative decreases with x, then you have to pick, or I should say, if your n plus first derivative is decreasing with x, you pick the left endpoint. Okay, and your m would equal the n plus first derivative at the left endpoint. If your n plus first derivative is increasing with x, then you're going to pick the right endpoint. And so your m will equal the n plus first derivative evaluated at the right endpoint. Okay, because that would be where your derivative is maximized, your n plus first derivative. Okay. And all right, so that's generally how you find M. Now, of course, there are situations, for instance, where you have a sine or a cosine involved. Whenever you have a sine or a cosine involved in your n plus first derivative, you'll replace sine or cosine by 1. You'll replace the sine or cosine by 1. And that's something you saw back in section 5.9, and you'll see an example of that as well. But all right, so that being said, I want to just kind of touch base. Are you feeling a little comfortable with finding this M value? Does this recap help a little bit? I'm just kind of curious. Maybe it does a little. How many does this help a little bit? Okay, thank you, Robin. Thank you, Tyreek. Great. Thank you, John. Excellent. Okay, well, let's continue. Into our section 8.8. In this example, I want to approximate the function f of x equals x times the sine of 2x by a fourth degree polynomial at a equals 0. Okay, let me give you a chance to copy that down. Okay, okay, so we want to approximate this function, f of x equals x times the sine of 2x by a fourth degree Taylor polynomial when a equals 0. Now, my first question for you is, when you have a Taylor polynomial at a equals 0, that's a special type of polynomial. What do we call that? What do we call a Taylor polynomial when a equals 0? That's right, Robin. We call it a Maclaurin series. That's right, Tyreek. Very good. So what we're really finding here is a Maclaurin series for x times the sine of 2x. And when you look at the formula sheet here, so everybody has the example copied all right? We're good? Okay. So when you look at the formula sheet here, so here's your Taylor series formula, and you're just going to apply the formula, but of course a is going to equal 0. All right, so that being said, this is really just a procedure where you just have to be careful when you do your computations. So, you know, f of x is x times the sine of 2x. You have a product. So when you take the derivative, you have to use the product rule. Okay. And then when you take the second derivative, you know, you just have to be careful taking your derivatives. That's really this is why I wanted to do a problem like this, so that you could, you know, say, well, hey, you know, Dr. Duty did it, so I should be able to do it too, right? Pick. All right. How many derivatives do we have to go out, by the way, on this? We want a fourth degree Taylor polynomial, right? Or sorry, well, yeah, it's a Maclaurin series, but fourth degree. So what's the highest derivative I need to go to? Who can chat it out for me? That's right, Tyreek, the fourth derivative. So I know you're looking at this, you're saying, man, you know, this looks kind of, well, yeah, you just have to do the work, you know, you have to. So I do the third derivative. Okay. And I'm really not, I don't, you know, I mean, you know how to take derivatives here. You're using the product rule, you're using the chain rule, you're using your rules for taking derivatives of sines and cosines. So, but what I want to do is I want to see if you can get the fourth derivative off of the third derivative, okay? Let's see if you can work it out and see if you get the right answer. Take a moment. Okay, so let's see. Here's your fourth derivative. Fourth derivative is negative 32 cosine of 2x plus 16x sine 2x. How many did get that? Maybe give me a thumbs up if you... Well, are there any questions so far? Okay, well, let me ask you now, what do we do with these derivatives? What do we have to do next? That's right. That's right, Tyreek. Plug in 0. Evaluate them at 0. So I do that. I'm just going to close the outer door here. I can actually. It's a pretty good game. Okay, are there any questions so far? Had to go and close a door in the house. My brother was playing a little video game, and I don't want the noise. I don't want the noise to carry into the recording. All right, we'll go to the next page in a moment. So sometimes the derivatives can be a bit involved. Like you're going to have a problem where you have, I believe it's e to the x squared, function like that, and you're going to have to go out maybe to the third derivative or fourth derivative, and you just have to be careful taking your derivatives. And it's a little bit tedious, but it's good practice, and it's necessary for showing the work and getting the right answer. So, okay. So may I move to the next page? Are there any questions at all? Okay. Okay. So now our function, which is x times the sine of 2x, is approximately, notice that's an approximation symbol there. It's approximately equal to your fourth degree Taylor polynomial. And all I'm doing is I'm putting in the values. I'm just following, I'm just following the formula here. I'm following the formula. Okay. And I notice that the first, or the function at a equals 0 is 0, the first derivative is 0, and the third derivative is 0. So of course that gets reflected right, in my answer. But you just basically follow the formula and you can't go wrong. So these Taylor polynomials are, or Maclaurin polynomials, that we're able to approximate a wider class of functions than we could do in section 8.6. Okay, now what I'd like to do, I would like to graph our function f of x equals x times the sine of 2x and our fourth degree Taylor polynomial, the approximation to this function, the fourth degree Taylor polynomial, which is 2x squared minus 4/3 x to the fourth. I'd like to just graph them on the same screen. And are there any questions before we go and do that? Are there any questions on the answer here? All right. All right. I'm going to move then to the so bring up your have your TI-8483 calculator here, and let's go ahead to the calculator. If everybody's good, everybody has it copied okay? All right. So let me bring up the calculator. Share application. Okay, so I'm going to type in my function. Hold on here. X times the sine of 2x and now I'm going to type in my fourth degree Taylor polynomial. So I've got to get used to these buttons a little bit. Okay. So what I'm showing you here, it's important. Well, I mean, I want to look at my function and I want to look at the fourth degree Taylor polynomial and just sort of get a visual feel for the function and its polynomial approximation. So on window, I'm going to say maybe go from maybe -5 to 5. Let's see here. X scale, why don't we let that be 1? And I'm just sort of, you know, picking a window. I'll probably have to alter it. How many notice that when they pick a window, oftentimes they have to alter it after they do the graph? I'm sure you've had that experience. Sure. Hold on. Let me see who commented there. Right. John knows what I'm talking about. All right. Now, also, I want to be sure that I'm not worried about this delta X or trace step right now. On mode, I want to make sure, okay, my calculator's in radians. Good. So, okay. Let's go ahead and do a graph of this. And there we go. Now, one thing on the, let me go back into mode here. I can see that I want to have thick. I want to change that. I had it back when we were graphing sequences. Okay, there we go. There we go. So let me ask you, without me even doing a trace or anything, is let me just see here. One moment. Is the red graph here, is the red graph the function x times the sine of 2x, or is the red graph the 4th degree Taylor polynomial? Now hold on. Yeah, I'm sharing, right? Let me just make sure I'm sharing it. Good, good. Yeah, I want to know, is that red graph there the 4th degree Taylor polynomial, or is it the function x times the sine of x? That's right, John. That's right, Josiah. Very good, very good. It's the 4th degree Taylor polynomial. So for one thing, the 4th degree Taylor polynomial, you know, 2x squared minus 4/3 x to the 4th, as x gets large, that x to the 4th term is going to dominate that polynomial. And since there's a minus in front of it, the polynomial is going to go negative as x moves away from 0. And you notice we're centering the window at 0 because we have a Maclaurin polynomial, you know, because a equals 0, right? Now, naturally, the polynomial and the function are approximating each other. Well, they're very close about a certain range of x, a certain interval about a equals 0. But then as you move out, as your x gets larger, the Taylor polynomial doesn't do well at all. So like, for instance, if you go past x equals 1 or -1, you know, if you're not going to use this 4th degree Taylor polynomial to approximate this function, because when x is larger than 1 or x is less than -1, the Taylor polynomial does not approximate the function well. And even before then, it doesn't. But I mean, I would say the polynomial seems to work well when x is between -0.5 and 0.5. But let me ask you, let's say you wanted your Taylor polynomial to approximate the function x times the sine of 2x better. What could you do? What could you do to get a polynomial that will be a better approximation further away from 0? Okay, so once again, at a equals 0, right there at the origin, the polynomial and the function, the polynomial approximates the function very well. But as you move out from the origin, the polynomial, Taylor polynomial, starts to fail in its approximation of the function. And certainly at x equals 1, the Taylor polynomial does not do a good job of approximating our function. There is an error there. So if I wanted to approximate my function at x equals 1, what could I do to improve my approximation? What could we do? So the fourth degree Taylor polynomial does not do a good job. That's right, Robin. Increase the degree of your Taylor polynomial. Very good. So if you were to do a 6th degree Taylor polynomial or an 8th degree Taylor polynomial, that polynomial will approximate the function x sine of 2x over a wider interval, for x. And that makes sense because you're taking more terms. I mean, you're taking more terms in your polynomial. So the more terms you take in the polynomial, I'm going to be careful how I say it. The more terms you take in the polynomial, the better the polynomial is going to approximate your function. Okay, and if you want to know the bound on the error in your, okay, let me stop the sharing here. If you want to know, if you want to have an idea of the bound on your error, you can use the Taylor inequality formula, right? You can use the Taylor inequality formula right here. All right. Now, of course, the tricky part of the Taylor inequality formula is finding that value of m. And for this function, x times the sine of 2x, well, I want to say this the right way. In WebAssign, for the problems where you have to use Taylor inequality, pretty much all of the functions, when you compute the appropriate derivative, the n plus first derivative, that n plus first derivative will either be decreasing or increasing, or in the case where you have an n plus first derivative being a sine or a cosine, you replace the sine or cosine by 1 to get your m value. For this problem here, where our function is x times the sine of 2x, it's the way the book does it is they use a graphical approach where they look at the function, the n plus first derivative. In this case, it would be our 5th derivative, right? To get the for the error bound for a 4th degree Taylor polynomial. You know, they look at the 5th derivative of the function, and based on the graph, they state what m is. But I don't want you to use I don't want you to have to use graphical means to find out what m is. I either want the n plus first derivative to be decreasing or increasing, or if it has a sine or cosine in it, you replace that with 1. Okay, so okay, let's do another one here. Are there any questions on this particular problem that we just did? All right, and I should mention too that it is nice to graph the polynomial and the Taylor polynomial and the function on the same screens, because you know it's also a way to confirm that your answer is right. You know, your polynomial should approximate the function pretty well over a certain interval, and if it doesn't, then you know there's an error in one of your terms. Okay, so that's just that's a value to you. Okay, let's do another example here. All right, let me give you a moment to copy down this problem. Okay, so in this problem, we want to use a fourth degree Taylor polynomial to estimate the cosine of 69 degrees. Okay, so this is actually this is an application that you haven't seen yet of a Taylor polynomial. So of course, things like, angles like 45 degrees, 60 degrees, 30 degrees, those are all where we can get exact values of sines and cosines. The cosine of 60 degrees is a half, right? The cosine of 30 degrees is √3/2. But how do you do the cosine of 69 degrees? How do you do that? How does your calculator magically, if you put the 69 degrees in your calculator and do the cosine, you magically get an answer? How does it do that? Well, or a computer. Uh, you know, how would a computer magically get that answer? Well, there are algorithms programmed in computer programs that can compute these trigonometric values, and the algorithms are based on something, right? Well, they could be based on Taylor polynomials. So, okay. Well, all right. It says use a Taylor polynomial, right? So a Taylor polynomial means we have to identify a value of A to use. Okay, and I'm going to note that, well, so, I mean, I need to have an angle where, to use, of an angle to let A equal. Okay, now I'm gonna write something here. Okay, I'm gonna write A equals 0, and what I'm doing, well, hold on. Let me write 3 values of A, and of course I'm working with radians, right? Taylor polynomials can be expanded around any A value you want them to be, but sometimes one A value is better than another A value. Let me see here. Let me put down 4 A values. Okay, so choice 1, 2, do the best I can here, 3, and 4. Using Roman numerals here. Choice 1, 2, 3, and 4. For being that we want to estimate the cosine of 69 degrees, what A value would maybe be the best to use? Choice 1, 2, 3, or 4? And all these A values are values that we can compute the cosine of easily. What value of A is going to make the most sense? Given that we want to, okay, Josiah says 4. And Josiah, why are you saying you're correct? Why is choice 4 your choice, Josiah? What's special about pi over 3 or 60 degrees? Why is that a better choice than the other 3? That's right, Josiah. Excellent. It's closest to 69 degrees. Pi over 3 in radians is 60 degrees. And that's closest to 69 degrees. So that's the value of A we choose. You notice in this problem, they're not telling you what value of A to choose. So you have to come up with the value of A, and it has to be the best value of A. So 60 degrees works. Pi over 3. Are there any questions before we move on? Okay. Well, let's go ahead and look at the solution. So, of course, you know, I have my formula sheet there. There's the Taylor formula for the polynomial. Okay, so since 60 degrees is the closest nice value to 69 degrees, sorry, since 60 degrees is the closest nice value to 69 degrees, we will expand our Taylor polynomial about A equals pi over 3. And they are looking in the problem for a 4th degree Taylor polynomial. So, of course, we have to go out for derivatives. And I have the little 30, 60, 90 right triangle here just as a reference. All right, I'll give you a moment to copy that down. All right, are there any questions so far? Okay, well, now that we have this, we're able then to write out our fourth degree Taylor polynomial, as you see here. So I'm just kind of letting you copy things down. Let me know if you have any questions. Okay. So the cosine of x is approximately equal to this fourth degree Taylor polynomial with these terms. And naturally, it's a natural thing to want to simplify all these coefficients. And certainly for your final exam, as part of showing your work, I would want to see you simplify all of these coefficients. Okay. You know how to compute factorials. So if I may, I'll move to the next page. Is everybody good so far? All right. So when you simplify the coefficients, this is going to be your polynomial. And it is a polynomial, right? We love polynomials because they're very easy to work with. All right, so take a moment to copy that down. Okay, so now we have our fourth degree Taylor polynomial approximation to the cosine of x. Notice I'm saying that the cosine of x is approximately equal to this fourth degree Taylor polynomial. We can't say equal because they're not equal. But hopefully with four terms in this polynomial, the fourth degree Taylor polynomial should be able to approximate the cosine of 69 degrees pretty well. But the formula itself, the fourth degree Taylor polynomial, in order to, what we want to do is we want to utilize it. We want to plug in an x value. But in order to do that, the x value has to be in radians. We can't plug in an x value in degrees. So that means what we have to do next is we have to convert the 69 degrees into radians. And so what we do is we multiply 69 degrees by pi over 180 degrees. So we can convert 69 degrees into radians. How many recall doing that kind of thing in trigonometry? Yes. Thank you, Robin. Thank you, John. Thank you, Tyreek. Absolutely. And now, you know, what you learned is coming back, right? All right. Thank you, Ryan. All right. So now what we're going to do is we're going to say, okay, well, the cosine of 69 degrees is the same as the cosine of 23 pi over 60 in radians. That's approximately equal to the fourth degree Taylor polynomial, t sub 4, at the value 23 pi over 60. That's the x value. And so what we have to do is just get this a little bit In the formula here, for x, we have to put in, everywhere we see the x, we have to put in 23 pi over 60. And that's what we do here. That's what we do right here in this step. That's what we've done. Okay, I'll give you a moment. I know there's a lot of copying, so. And this is, again, the kind of work you can be almost sure on the final exam you're going to see a problem or problems like this, and I want to see the work. I don't want to just see an answer at the end. I need to see the justification that you understand the concepts for the problems. So this work is very important. Okay, now to simplify our life, you notice you have the 23 pi over 60 minus pi over 3, and you see it 4 times. Well, when I compute this approximation, I don't want to have to always be subtracting. I don't want to do this subtraction 4 times. So I note that 23 pi over 60 minus pi over 3, okay, is the same as 23 pi over 60 minus 20 pi over 60. I get the same common denominator. That gives me 3 pi over 60, or pi over 20. So everywhere we have 23 pi over 60 minus pi over 3, everywhere we see that, we can replace that with pi over 20. And so this gives us a simplified thing to compute. Because what's next is we have to compute this on our calculators. And what I'd like you to do after you copy this down right here, I want you to, on your calculator, work this out on your calculator and compute the answer. Okay? Even though it can be done by hand, it would take quite a while to do by hand. But at least it's doable, right? So take a moment to compute it. I want to see if you get the answer that I got. All right, so this is the answer that I had gotten, I should say. Okay, Tyreek, I was glad. I want to see if, let me write down Tyreek's answer, because I'm actually, hold on, Tyreek, one moment. I want to see if Tyreek's answer is confirmed when you compute this out. And please, Tyreek, I trust you worked this exact thing out, all typed it in your calculator, and got the answer. You got 0.35836864. Maybe give me a thumbs up on that if. Okay. All right. Well, let's see, Tyreek, if that's confirmed by another student. Okay. Thank you, Robin. Same thing. All right. So my answer isn't quite right here. My answer, I'm kind of glad about this because now let's see. 3, 5, 8, 3. Looks like Robin's agreeing with you. 0.3583 6, 8. Okay, we'll say 686. We'll stop there. And actually, let me change it on my little sheet here. 0.358 0.358 3686. Okay. Who else got something like that? If you would maybe just give a chat out. If okay, John did good. Thank you, John. Francesca, thank you. Same thing. Okay. All right. So, well, all right. So now what we want to do is find out, okay, we want to find out how accurate is this estimate. So you have to think it, I mean, this kind of application would be relevant, for instance, to astronomy. In astronomy, if you're off a little bit on your angle, you'll when you're looking out in space, you'll miss the planet, right? Little errors in astronomy mean big mistakes. So of course we want to know how accurate this estimate is. Do we need, you know, is the level of accuracy good enough for our purposes? And of course, we're going to use Taylor's inequality. So section 8.7, you are using Taylor's inequality to answer the questions. So on that note, let's go to the next page. Okay, how accurate is this value, this approximation? T4, fourth degree Taylor polynomial evaluated at 23 pi over 6. Well, again, by Taylor's inequality, okay, we're trying to get a bound on the error, which is the difference between the fourth degree Taylor polynomial and the cosine of x. The error bound is going to be m over 5 factorial You see, since we had a fourth degree polynomial, we use 5 factorial times absolute value of x minus pi over 3 to the 5th power. So what we have to find out is what m is, and we have to put in a value for x minus pi over 3. Well, we know that the fourth derivative was the cosine of x. So the fifth derivative is negative sine of x. And we are trying to find out where the absolute value of the fifth derivative is maximized. For what value of x is that maximized? Well, I haven't given you, I want to be careful here how I say it. It isn't like we have a range of x where we can see, well, I want to say it's the right way. Normally what we would do is we would have some range of x, and we would look at this absolute value of negative sine of x over the range and see if that is increasing or decreasing over the range of x, and based on that we would put a next value in. However, we want to keep things easy, okay? Using Taylor's inequality in relation to section 8.7, we want Taylor's inequality to be easy to apply, even if we're not exactly going to get an exact correct error bound. So, hey, the sine, cosine, negative sine, negative cosine, well, in this case, the absolute value of negative sine of x is the absolute value of sine of x, right? But the sine of x never goes, it's never, the sine of x, I want to say, the absolute value of the sine of x is always between 1 and negative 1. So the absolute value of the sine of x is never going to be more than 1. So to make things easy, we'll just take n equal to 1. And so then the remainder, okay, the error in our approximation is going to be less than or equal to 1 over 120. Again, that 1 there is your m value. Okay, 1 over 120 times, now the x minus pi over 3, well, x we're using is 23 times pi over 60, so that's what we're going to put in for x, 23 pi over 60. 23 pi over 60 then minus pi over 3 raised to the 5th power. Okay, and that's going to get us this. So we're going to get 1 over 120 times pi over 20 to the 5th power. And I'm computing that just like you, just to double check my work here. And you should get 7.97 times 10 to the negative 7th power, which is going to equal that decimal, 0.000000797. Okay, let me know if you have any questions up to here. Okay, and so I note that this is less than 5 over 10 to the 6th power. So our cosine of 90 degree, the estimate cosine, well, hold on. So our cosine of 69 degrees estimate using the fourth degree Taylor polynomial, which was 0.358, 3686. 0.3583686. Our approximation should be therefore to 5 decimal places. And on your TI-84, what I'm doing now is I'm going to compute the cosine of 69 degrees on my TI-84. I'm just curious what the calculator gives you, and of course I have to be in radian mode, degree mode for that. Okay, so the calculator gives 0.358 3 6 0.35836 79 0.35836 79. And I won't worry about the well, got to be a little bit careful here. So, oh, okay, I'm liking this. I'm liking this because if you round this to 5 decimal places, if you round the calculator answer of 0.3583679 to 5 decimal places, you're going to get 0.35836. Well, I want to be a little bit careful here. The first, okay, no, I want to say that we're okay. The first 5 digits, 0.3, so forget about what I just said there. The first 5 digits, 0.35836, agree. So our approximation for the cosine of 69 degrees, I mean, let's assume the TI-84 calculator is giving a very, very accurate answer for the cosine of 69 degrees. Well, our approximation, our Taylor polynomial approximation of 0.3583686, the first 5 digits of our approximation, 0.35836, agree with the answer that the calculator gives us. Okay, and if we were to, do a 5th degree Taylor polynomial or a 6th degree Taylor polynomial, we would get more agreement in digits. But we do have an estimate that's correct to 5 decimal places. Okay, are there any questions on that? How many think this is a really cool application? Thank you, Josiah. Thank you, Tyreek. Excellent. Just a few people. We have some. Thank you, Robin. Thank you, Francesca. Excellent. Yeah, I mean, this is, thank you, John. I mean, this is really beautiful stuff. And it's allowed mankind and womankind to advance in mathematics, to advance in life. Thank you, Ryan. I mean, you know, we live very differently than we did 300 years ago. And of course, it's largely because of technology. But technology, to develop technology, you need mathematics. And and for mathematics, you need to be able to approximate things, approximate values. And so mathematicians came up with these concepts, and they're very helpful. Okay, let me put a stop on the recording here.